To summarize, we have free fall when the only force acting on the object is gravity, and it does not matter whether the object is going up or down. The acceleration is always equal to the gravitational field G, which is pointing downwards at the surface of the Earth. Now, the value for G, when we express it in meters per second squared, at sea level is 9.8 meters per second squared. That's the magnitude. The direction is towards the Earth. In most of the problems, we'll be using 10 meters per second squared for simplification. Now, in questions, you'll be told if it is either 10 or 9.8. If we choose the upward direction as positive, since all motion is along one direction, if we choose up as positive, then our acceleration is minus 10 meters per second squared, since our acceleration is pointing downwards. A few questions. If we have a ball and a feather, this is the feather, this is the ball. Which will have the larger mass? You know, really, this is a funny kind of question, but I'm starting with it purposely. Let's assume that the ball has a larger mass. Which will have the larger acceleration? So the order of the questions is a little odd. What will have the larger acceleration? Neither. If they are in free fall, they both have the same acceleration, 9.8 meters per second squared, in the downward direction. Now, when do we have free fall? When the only force acting on the object is the gravitational force. That does not happen at the surface of the Earth. Why doesn't it happen? It does not happen because at the surface of the Earth, in addition to the gravitational force acting on the object, we are going to have an air resistance force acting on it. So the overall net force on an object falling at the surface of the Earth is not the gravitational force. It is the combination of the two. So at the surface of the Earth, we don't have free fall. That's why at the surface of the Earth, the feather is going to have a different acceleration than the ball. Now, for objects for which air resistance is really small and can be neglected, we are not going to notice that. For example, if we have two different balls, we're not going to notice the effect of air resistance. But when objects have quite different shape and quite different mass, the effect of air resistance is going to be prominent, and that's why at the surface of the Earth, the feather and the ball are not going to have the same acceleration. But here the question is asking about free fall, like if we were at the surface of the moon, where there is no air. Then they both have the same acceleration. At the surface of the moon, of course, it's not going to be 9.8 meters per second squared. It's going to be 1/6 of that. On Earth, we can have an experiment like that, and actually you can search in Google, on YouTube, for example, and find videos that show you that. We can have both the feather and the ball in a container, and we can evacuate it. We can remove the air from it and let them both fall, and you'll see that they'll fall with the same rate. So they'll have the same acceleration, the same velocity, and they will have hit the ground at the same time. One more thing here. Remember the equations for constant acceleration? We have constant acceleration here. Our acceleration, if we use it along one direction, is minus 10 meters per second squared. or minus 9.8 meters per second squared. So we are essentially in this domain. Motion along one direction, usually since motion is along the vertical axis, we might be using y instead of x. So everything is a y instead of x. And then my acceleration is just that, the minus 10 meters per second squared. These are the equations we will use for freeform motion. One last point here. What are the initial and final velocities for freefall? It's not something that we usually know unless it is given. The initial velocity, a word that you look for in problems when they say dropped, or let go, or something similar, that immediately tells you that the initial velocity is 0. If it is something that is thrown, tossed, or something similar, then they might tell you what the initial velocity is, or they might ask you to find it. If they ask you to find it, we have the equations here. That's what you need to use to find it. Final velocity, same thing. Be careful here. One common error that people make is to say the final velocity is 0. Now, if I drop an object from here, it's going to fall, it's going to bounce back, bounce back, bounce back, and then eventually it's going to have a final velocity equal to 0. That's after several bounces. A lot of things happened here, but usually when we study physics, we study things but usually in physics, we break motion one part at a time. For example, here, the fall, the free fall part. That's from the instant this object was here till it is about to touch the floor. That's the final velocity, when it is about to touch the floor. Subsequent motion are different problems, are not part of the free fall. There is another force that acted here from the floor on the ball that made it not a free fall anymore. So free fall is from the instant it is here till just before it got touched by the floor. That's when we have free fall. So final velocity is a quantity that we are going to need to find.